Hi everyone, welcome to part 3 of lecture 4, and we will continue to discover some important discrete distribution, and in this part we will cover the binomial distribution. So actually the binomial distribution is very similar to Bernoulli distribution, and just remember what was the Bernoulli distribution. So that was a distribution with only two results, with the probability of success and probability of failure, right? So as similar to Bernoulli distribution, the binomial distribution also has only two possible results. But in this case, the number of trials are some constant number, like it is known in advance, okay? So let's say the n trials. For example, the total number of heads in n flips of a coin. So in this experiment, we know that the total number of trials, okay? If this is the case, we can say that X is said to have a binomial distribution, okay? And we will denote this X has binomial distribution with the parameters n and p. So what was the n is the number of trials, and the p is probability of success. So if that is the case, is that possible to calculate the probability mass function of X? So before going to details of PMF, let's use some sequential trees to understand the whole process. Let's say the number of trials in tossing a failed coin is tossing a coin. We don't know if that is failed or not. The number of trials is 3, and let's say the probability of success is p. So if we show this experiment with 3, how we will start? Let's say this is the start point, okay? With the probability of p, the upward phase will be heads, okay? This is the first possible result. And in my second trial, with the probability of p, I will get again heads. And with the probability of 1 minus p, I will get tail. In my third trial, with the probability of p, I will get heads. And with the probability of 1 minus p, I will get tail, okay? And I can do same thing all the branches, okay? So let's focus on, let me change the color, this branch. Let's say this is one of the possible results, right? And what was the total possible results is 1, 2, 3, 4, 5, 6, 7, 9, right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8. So okay, so let's okay, let's focus on one of the possible results, right? This path is one of the possible results, right? So if this is the case, how can I calculate the probability of these results? At the end of this experiment, I will get 3 heads, and each of them has the probability of p. So I can simply calculate p times p times p, so which is p to the 3. Okay, this is the simple probability. So this is how actually we calculated the results, right? The probabilities of each possible events. So, but this is easy to show you when the number of trials are respectively small. But let's say n is 10,000, and in this case, it's not easy to draw some trees, right? But did you notice some pattern here? let me the first, let's look at this branch as well. Like, let's start from here, here, and here. So this is also one of the possible outcomes. So what is the probability? The p times 1 minus p, right? So that is p to the 2 times 1 minus p. So we can do it for every possible results. We can calculate, and did you notice something here? There is some particular pattern here. For example, here we have 3 hats, and the probability goes p to the 3. And we have 2 hats, 2 success, and 1 fail. And it goes to p to the 2 times 1 minus p, which is actually the success times failure. So actually, there's a pattern here. Let's look at the last one, the tail, tail, and tail. This path, okay? This path. Tail, tail, tail. So, which is actually the fail times fail times fail, right? And what is the probability of fail, which is 1 minus p, right? So 1 minus p times 1 minus p times 1 minus p. So it will be 1 minus p to the 3. So that's why by multiplying the conditional probabilities along the corresponding path of 3, we see that any particular outcome that involves k hats, it can be 1, 2, 3 in our case, and 3 minus k tails, right? So k success and 3 minus k fail has the probability of p to the k times 1 minus p to the 3 minus k, right? This is the probability of some particular paths for the given for the required number of success. But here there is something. Let me look at here. Let's say we want to here. Let's say the k is 2. So what's that mean? We have to calculate the probability of the branch that will produce 2 hats. Is there only one branch? No. We have different branches, right? Like this is the first one, this is the second one, I think this is the third one. So we might have more than one branches. So that's mean we have to calculate, we have to consider all possible branches. How can we do that in an easy way? It's not, if the n is big number, it's not easy to draw all these 3 things, right? But there is some easy way. So we can calculate actually. We can calculate how many branches we have. Okay. So this is n choose k will give us the possible branches, right? So if I say, for example, the 5, 2, it will give me how many different branches that will have 2 hats, for example. Okay. So let's do this 3, and it will be more concrete. That's mean I have 3 branches. I mean 3 paths actually, like this one, like 1, 2, and 3. 1, 2, 3. Okay, 1, 2, 3. So we have 3 distinct stage. And how many of this stage will consist two hats. For example, one hat here, one hat here. Okay, so I will, if I go with this path, these pages will include two hats. So that's why this is the easy way to calculate how many branches we have. So let's say we have n choose k branches, right? And how can I calculate the total probability? Simply, which is the number of branches times the corresponding probability, right? So what was the corresponding probability, which is here, p to the k times 1 minus p to the 3 minus k, which is the probability of only one branch, and how many different branches we have, and choose k. So that's why if you multiply this, it will give us the probability of x is equal to k, which is equal to PMF of k. Okay, so this is how we calculate the PMF. So is this a proper probability mass function? To answer this question, we have to check some properties. The first one is the PMF of k should be positive, right? So in our cases, this one, the PMF of k is the non-negative, because this is a positive number, this is a positive number, this is a positive number, so we will get a positive number, right? So that's why we satisfy that properties, that condition. The PMF of k is non-negative. And also the total probability should be equal to 1, right? So this is the PMF for one single values, and the k can get different values from 0 to n, right? So if we sum all these probabilities, we can to calculate this part, we can use this formulation. You can remember it from high school math or the calculus math. The formulation is p plus 1 minus p to the n. So the p's will be cancelled, and the total value will be 1. So that means the total probability will be 1. So that's why we satisfy this condition as well. So we can say that this probability mass function is proper. And this is called the binomial expansion, and that's why there's distribution called the binomial distribution. Okay, you can check this formulation. So let me show you this distribution in a graph. Let's say this is the first one. In this case, the number of trials is 20, and the success probability is 0.5. And this shows number of the probability of number of success will be 0. Okay, so how we can calculate this one? So the first is n choose k times p to do k times 1 minus p n minus k, right? Let me double check this one. There's one, right? So how many trials we have in this example? 20. So it will be 20 choose k. K in this case 0. Okay, 0 times what was p, which is 0.5. So 0.5 to the 0 times 1 minus p, 1 minus 0.5 to the 20. Okay, so this is the corresponding probability here. It is this point. Okay, so for each one, for each k, I can calculate corresponding probability. So I hope it's clear and you can make same graph, same calculation. So this is another example. In this case, the number of trials are same, but the probability of success are different. So this example actually really good to understand the logic behind the variation in the probability. Okay. So this failed points corresponds to this distribution, this binomial distribution, and that circle, the empty circle points, corresponds to the second distribution. First, look at the first one. So, for example, this point corresponds to the probability of the number of success will be 0. Okay, so for this distribution, for this guy. And this points corresponds to the probability of number of success will be 0 if that random variables have this binomial distribution. So let me clearly explain this part. Here, in the first one, let me clear what I write here. In the first one, being successful is not easy, right? Is not easy. That's why getting 0 success will have high probability. On the contrary, in this distribution, getting success is most likely, right? So that's why getting 0 success will be less. So that's why you can understand the relationship between the PMF and this probabilities. That's why there is no symmetry in this distribution as opposed to this one, because this one is 0.5, and we will see some symmetric distribution. Okay, but in this one there is no symmetry. This one will decrease, and this one will increase. Okay, so that's you can think again why and how these probabilities affect this this number of success. Okay, so I hope you will understand and it will be more clear. So let's look at the expected value. So remember that the expected value is simply the E of x is equal to x, the sum of, let me write in a good way. Expected value of x is equal to the sum of x time PMF of x, right? So we know the x's here, which is k, all possible k is from 0 to n, and this is the PMF of our random variable, right? So we just give that here. Okay, yeah. So now I will just do some trick, but nothing. We give the first value of k, which is 0. So what will be that? 0 times something, right? This part. So it will be 0. So that's why I can cancel this first value, and I can start from 1, right? K is equal to 1. K from 1 to n, and I will calculate the same thing. Now let's look at another trick here, and let's rewrite this part as this one, the k times n factorial times n minus k factorials times k factorial, right? And this k factorials also can be k times k minus 1 factorial. This case will cancel each other. And let's rewrite this one as n times n minus 1 factorial divided by n minus k factorial times k minus 1 factorial. So this part is actually n minus 1 choose k minus 1. You can check it by yourself, okay? So I can rewrite this part as n times n minus 1 choose k minus 1. And this part is same. Now, because this is a constant value, the n, it can go out, okay? And also, let's reduce the number of p by 1. I mean, let's do this here, like p times p k minus 1 times 1 minus p times, let me write this one as n minus 1 minus k minus 1. It will be same, right? This is the ones will be cancelled. So this part is actually same n minus k. Okay. So what I did, I just got 1p as well, and went to do and send it to the outside of that summation. It will be np here, and my new multiplication will be like that. So let's say n minus 1 is m and k minus 1 is j. So it will be p to the m times 1 minus p to the m minus j, right? So this is also the PMF, right? PMF, the probabilities. So what was the total probability? Which is equal to 1, right? So that's why. So this part, for example, if j is 0, that is the probability for the random variables equal to 0. And I will look that, or I will sum all the probabilities for all random variables. The summation will be 1. That's why this part will be 1 and the result will be NP. So the expected value of X, which has a binomial distribution with the parameter N and P, the expected value of it will be N times P. So how we can calculate the second moment? We will do same thing actually. Let's again ignore the k is equal to 0 and start from 1. It will be k squared and the PMF. And we do same thing here. Here we write this part, okay? This part is with that here the k times nk, right? Okay. This part is this one, right? So k times n choose k, and you know what we did, what trick we did for this part in the previous slide. So it will be k times n minus 1 choose k minus 1, and this part is same. So again, we can reduce the p by 1, and this np will go outside of the summation, okay? And it will be np sum k times n minus 1 choose k minus 1 p to the k minus 1 times p minus p to the n minus 1 minus k minus 1. So again, let's say n minus 1 is m, k minus 1 is j. It will be something like that, okay? Now, because there's a summation here, I can split this summation like this one, okay? Because this is the summation here. I can rewrite this part for j and for the 1 actually. So here what I mean, this part, let's say this is an A. Actually, what is this? This is summation j from 0 to n, which will be j times a plus 1 minus a, right? And also this can be written as summation ja plus summation a, 1a. And this is what exactly what I did exactly here. Okay, this is the first part. This coming from j times this part, and this part is coming from 1 times this part. So, and what is this one? This is the expected value of the binomial distribution, right? Because this is a new binomial distribution with the parameter m and p, right? And what was the expected value is np, right? That was the number of trials, and in this case, number of trials is m. So that's why this is np. And what is this one? This is again the summation of all probabilities, and it will be equal to 1. That's why this will be mp plus 1. So if you do some math operation, you will be ended up with n squared times p squared times npq. And this change. Okay, so this is the value of second moment. Okay, so how we can calculate the variance, which is the expected value of x squared minus expected value of x squared. So we know this one, we just calculated it, this one, okay? And we know the expected value of x, which is mp, and let's square it, and we will end up with npq. So this is the variance of the binomial distribution. So let me give you some quick informations about the binomial distribution. We can think of binomial variables as the sum of n individual identical distributed Bernoulli random variables. Okay, so if this is the binomial distribution, we can think that the sum of n individual identical independent distributed Bernoulli random variable. Okay, so the expected value of x, which is a binomial, which has binomial distribution, is the sum of individual expected values of binomial variables. Okay, and we will prove that later. So which is p plus p plus p plus, and it will be np. The last one is the variance of x is the sum of individual variances since xi are independent. And what was the xi, which is the binomial variable iid, independent identical distributed. So, and here, please keep in mind, if those binomial variables are not independent, this will not be valid. Okay, so in this case, being independent or not is not important, but here, which is the key point, the xi's should be independent. And what was the variance of binomial variables? We just calculated in previous part. That was p times q, and we will sum npq's. It will be n times pq. Okay, so let's look at the one example. So let's say it's known that any item produced by a certain machine will be defective with the probability of 0.1 and independently of any other item. Okay, so that's mean the defection rate is 0.1. So what is the probability that in a sample of 3 items, at most 1 will be defective? Here, that is a non-negative word. You can think that that's a failure. I mean, you can relate it with the failure, but that is not the point. The point is the success and failures actually related with our interest. Okay, so that's why in this case the detection will be the success of success for us, because this is what we looking for. And also, what is the expected number of defective items? So actually this is the expectation. So the number of defective item X has a binomial distribution. So what? Why? Because we have two results, only two results, which is a failure and success. These are the independent and identical. The probability will not change. And also we know number of tries, 3. Okay. So n is 3, the p is 0.1, which is the probability of success, and desired probability is p, the probability of x is equal to 0 plus probability of x is equal to 1. Why? Because we are asked at most 1 will be defective. So 0 and 1, at most 1. In other words, the x will be less than or equal to 1. So let's do it first. This one, x is equal to 0, which is 3 choose 0 times the p, which is p, 0.1 to the 0, okay, times 0.9 to the 3, plus this one now, 3 choose 1, 0.1 to 2, 1 to 1, and 0.9 to the 2. And this will give us the 0.972. The total probability. The probability of x will be less than or equal to 1. Okay, so what was the expected value of a binomial distribution? That was n times p, right? Remember it, or just check the previous slides. What is the expected number of defective items out of 3 items? Okay, so n is 3. The probability of detection is 0.1. This is the probability of our success, and it will give us 0.3. So that is the expected number of defective items. Okay,